Okay, welcome to week 4. So in week 3, we looked at the breadth-first search algorithm, which starts from a particular node in a graph and steps out one step away from that node, then 2 steps away from that node, then 3 steps away from that node. You can think of that as being sort of like searching a sequence of concentric circles moving out from the source node in order to find the shortest path to some target. This week we're going to take a look at depth-first search, which takes the opposite approach of breadth-first search. Whereas breadth-first search exhaustively visits all of the one-step neighbors first, and then exhaustively visits all of the two-step neighbors and so forth, depth-first search starts with a one-step neighbor, then immediately jumps from there to a two-step neighbor, and from there to a three-step neighbor, and so on, until we hit a node that has no unvisited neighbors, and then we backtrack up the path that we have made, up the tree that we have made, until we find a node that does still have unvisited neighbors, and we plunge downward again from there. So visually, you can think of breadth-first search as sort of like the concentric rings that you get when you toss a rock into a pond, whereas depth-first search is more like a jagged lightning bolt with several branches that come down and abruptly stop. All right, so here on slide 2 is the graph of friends that we used in the previous lecture. Depth-first search is similar to the in-order traversal that we did with the binary search tree. That is, when we displayed the values in a binary search tree in order, our algorithm was first display values that are to the left of the current node, then display the value that's in the current node, then display the values that are to the right of the current node. This kind of naturally recursive definition is how we will implement our depth-first search. So, for example, looking at our graph, again, let's imagine that I'm starting from me in order to make sure that I am systematically visiting all of my neighbors. I'm going to start from me and visit the neighbor that's earliest in the alphabet first. So I'll go from me to A. Now in depth-first search, having reached A, I immediately go to A's next neighbor in alphabetical order, so that's B. All right, so I've gone from me to A to B. Now when I hit B, B has no unvisited neighbors, so I have to backtrack to see whether A has unvisited neighbors. Indeed, A does have an unvisited neighbor, so the next node I go to from A is J. J has a ton of unvisited neighbors. We'll handle these in alphabetical order. From J, we'll go to E. From E, we'll go to F. From F, we'll go to M. From M, we have a choice between S and T. We'll go to S. Then from S, we'll go to G. From G, we will go to Ed. From Ed, we have a choice between R and Z. We'll go to R. And once again, we hit a point where we have to backtrack because R has no unvisited neighbors. So we come back to Ed. We visit Z. Now, S has already been visited. So from Z, we're going to go to Y. And then to Q. And then to I. Well, I, at this point, has no unvisited neighbors, so we backtrack to Q. We visit X. X does not have any unvisited neighbors, so we have to backtrack quite a bit now. We backtrack to Q, and then to Y, to Z, to Ed, to G. And G has an unvisited neighbor, so we go to K from G. Eventually, this breadth-first search algorithm will visit every node in the connected component that includes me, but it's doing downward depth-first searches rather than outward breadth-first searches in order to accomplish this. Now, it is possible to define the depth-first search algorithm iteratively. Basically, it's very similar to the outline of the breadth-first search code, except that you use a stack to contain unvisited nodes rather than a queue. In fact, as a general thing, if you have a recursive algorithm and want to turn that into an iterative algorithm, you frequently end up using a stack to support that. In effect, what you're doing is you're trading having a stack in your own code versus using the system's stack of symbol tables from function calls. Depth-first search, just like breadth-first search, is useful for identifying connected components. Either algorithm works fine for that. Depth-first search is better if you're trying to find something like a solution to a maze. If you're trying to get through a maze, you don't necessarily care about finding the shortest possible path through the maze. You just want to find a path as efficiently as possible. And it turns out, on average, that depth-first search will find a solution to the maze by visiting fewer total nodes than the relentless outward behavior of the depth-first search algorithm. Basically, any algorithm that requires backtracking, that is, you attempt to find a solution, you discover you can't go any further, so you back up and try another path, is where depth-first search comes in. Now, on the other hand, depth-first search is not at all useful for shortest path analysis. Depth-first search will find a path if a path exists, but offers no guarantee about whether that is the shortest path or not. Okay, so let's take a look at some almost working code for depth-first search. This is not quite working, but it's close. We have S, our set of nodes that we have visited. Of course, that starts as an empty set. We also have T, which is the tree of nodes that we have visited, starting from some root that we select. Here again, the tree is initially empty. And here's our depth-first search algorithm. The arguments are the representation of the graph, as we've had in the previous lecture. That is, the graph is a dictionary mapping each node to its directly connected nodes in alphabetical order. We specify the current node that we want to do our search from, and the parent from which we arrived at that current node. Now, let me skip ahead a slide, and we'll see that to kick this off, we specify our dictionary. We specify me as the current node, and me has no parent, so none is going to be the value of our parent when we're constructing this depth-first search tree starting from me. Okay, now, if the current node has not already been visited, then we're going to add the current node to the set that have been visited, and we're going to add the current node to the tree with its parent as the parent. Then, for each node in the immediate neighbors of the current node, and we've been careful to build our graph in such a way that these are alphabetical. At some level, that doesn't really matter. It really just has to be an exhaustive list of all of the immediate neighbors. So for each neighbor of the current node, we're going to call DFS again with the neighbor as the current node and our own current node as the parent of that neighbor. And this recursion will go down through the tree until we eventually hit a node that is already in our set of visited nodes, at which point we will backtrack up the recursion. All right, so here on slide 5 is what we get when we call this algorithm for the first time. The tree just contains me. The parent of me is none. I should perhaps have written none here as the parent of me. And the set of nodes that I visited so far is just me. Now, recall from me that we're going to visit me's immediate neighbors alphabetically, so we're going to visit A first. And in the recursive call, we're going to visit A's immediate neighbors alphabetically, so we'll visit B next. When we hit B, B has no unvisited neighbors, so we have to backtrack. Here's what that first downward branch looks like. From me, we visit A. We add A to the tree with me as the parent, and we add A to the set. From A, we visit B. We add B to the tree with A as the parent, and also add B to the set. And now we have to backtrack, so we come back up to A. From A, the next alphabetical unvisited neighbor from A is J. And so we visited J, and that led to a quite long branch in our tree. From J, we went to E, then to F, then to M, then to S, then to G, then to Ed, and then to R. And when we got to R, we had to backtrack again. So we have this long downward branch in our depth first search before we have to backtrack. We backtrack up to Ed, and then we visited Z. And this backtracking continues, so we end up with our entire tree looking like this. When we backtrack to Ed, we find Z as an unvisited neighbor. From there, we visit Y, Q, I, backtrack to Q and visit X. Then we have to backtrack all the way up to G and visit K. Backtrack up to M and visit T, backtrack to J and visit L and W, and finally we end up backtracking all the way up to me and visit N and V. So what we can observe here is that depth-first search trees tend to be fairly tall and skinny with a small number of long branches. Breadth-first search, on the other hand, because we have to go out one step at a time in exhaustive fashion, breadth-first search trees tend to be fairly short and thick. Our depth-first search starting from me has found one connected component. If we want to find all the connected components using depth-first search, then we can simply traverse through the nodes in our graph. We'll discover that A is already in the set that we visited, B is already in the set that we visited, C is not in the set that we visited, shown here on slide 8. And so we build a new depth-first search tree starting from C as the root. Once we've done that, we'll discover that we have visited all 28 nodes that exist in our graph, and so we're done. And we have found 2 connected components in our graph. And here in slide 10 is the same diagram that we saw of the connected components that we found using breadth-first search last week. So, given a graph, when might you use breadth-first search? When might you use depth-first search? Well, breadth-first search is good if you need to find the shortest path that exists between some source and some target. That is, if you have your house at some location and your job at some other location, and you need to find the shortest path, whether that's by miles or by time, between your house and your job, that's not going to change very often, so it's probably worth spending the effort to figure out what the shortest possible path is. In fact, if you use an application like Google Maps to find the shortest distance between 2 points, this is how that's done. For example, here I've redisplayed slide 24 from last week's first part lecture. This was our shortest path tree from me to Ed, and gave me a path in which there were 6 nodes, me, I, Q, Y, Z, Ed, connecting me to Ed. On the other hand, we had to build a 20-node tree in order to find that shortest path. Now, using depth-first search, on the other hand, here I've displayed slide 7 from the current notes. It turns out that we only had to construct a 10-node tree in order to find a 9-node path from me to Ed. So the entire tree that we needed to construct was only half as large, although the path is a little bit longer. Okay, so our path is me, A, J, E, F, M, S, G, Ed. And we have found a solution for getting from me to Ed. Of course, this is one example of DFS doing a faster search than BFS. It's not proof. Okay, our next topic is regular expressions, which are a sort of mathematical style notation that you can use for matching patterns in text. Originally, regular expressions were developed in the context of parsing human languages. In the 1960s or so, regular expressions were borrowed by people working on programming language design and compilers as a powerful and convenient way of describing language grammars, and also so-called lexical analyzers or parsers for different programming languages. I will confess to you here that regular expressions is one of the things that I'm glad I know quite well, because it saves an enormous amount of time and pain when you're dealing with large amounts of loosely structured data. Now, Python has quite an extensive collection of special characters that you can use within regular expressions. We are going to concentrate on the basic regular expressions and a few of the extended regular expression characters, which will give you the power to do most things that you need to do. I'm not going to try to do an exhaustive survey of all of the different regular expression tools that Python provides. So here on slide 13 are what are traditionally called the basic regular expression characters. These go back to early compilers, parsers, and user-level tools found in the Unix operating system, and perhaps even earlier than that. To illustrate how these basic regular expression characters work, we're going to take a look at a silly poem that has the advantages of being somewhat funny, short, and therefore easy to remember, and it offers some amount of variable structure. For example, some of the lines are indented, some of the lines are blank, one of the lines has a first non-white space character that's lowercase, one of the lines has no alphabetic characters in it at all, and so on. So, in a Python program called poem_regex, I've taken the lines of this silly poem and stored them into a list of lines named poem. In order to be able to use regular expressions on the lines in the poem, I have to import the RE module. RE for regular expression, and of course the name itself is so short that we don't need an abbreviation. The first regular expression character that I'm going to make use of in this pattern that I'm searching for is the caret symbol, or the hat symbol, or the circumflex symbol, or the up arrow symbol, or whatever you want to call that thing. We'll just call it the caret. And what it does is to search for some pattern at the start of a string. In this particular example on slide 15, my pattern is saying I want to look for lines that start with a capital H. So, for each line in the poem, okay, and my poem is a list of strings, so each line in the poem is a string, what I'm going to do is to use the search function defined within the RE module to search for this regular expression pattern in the current line. If that regular expression pattern is not found in the line, then the search will return none. On the other hand, if the regular expression pattern is found in the current line, the search will return something other than none, and in that case, I simply want to print the line that matches that pattern. So the upshot, since I am looping through all of the lines in the poem, is that I'm going to end up displaying all of the lines from the poem that begin with a capital H. Let's see that happen. Here on the right side is my poem regex program with my list of strings containing my poem. I've imported the regular expression module, set up my pattern, and now I'm going to search for that pattern in each line from the program, and let's see what we get. I'm going to press F5. There we are. So in the poem, let me just back up a moment. The lines that start with a capital H are the title line and the first lines of each of the two stanzas in this poem. Now, one thing to notice is that there's another line whose first letter is capital H, but the meaning of the caret symbol in regular expressions is very strict. It means that only a line whose first character is a capital H is going to be considered a match. In this particular line, the first character in the line is actually a space character, not a letter, so that's not a match. Okay, before we continue looking at these other basic regular expressions, we need to deal with a strange little wart in regular expression notation, which is the meaning and use of the backslash character. So in a regular expression, the backslash turns off the special regular expression meaning of whatever the next character is. Now let me show you some examples interactively to demonstrate. If I say S gets ASDF caret, well, now S is a string that contains a caret. If I try to say something like re.search caret in S, this is going to return something to me that's not the value none. That is, it returns to me something called a regular expression match object, and I might be tricked from this search into thinking, oh, that confirms that S contains a caret. However, if we look inside this match object, notice that the span is from character sub 0 to character sub 0. What that means is that S starts. Okay? So the caret symbol is looking for the start of the string, and any string starts. Therefore, no matter what the string is, if I search for caret in the string, I'm going to get a match. In fact, let me search for caret in the string, gibberty, all right? So there's no caret symbols in that string. However, the string does start, and so I do get a match. If I say re.search for a caret in the empty string, well, the empty string contains no characters, but the empty string does start, so I get a match. All right, so what I need to do if I want to search for a caret symbol in a string somewhere, I need to do a search for \caret in my string S. So the backslash is going to cause the caret to be treated not as a regular expression character, but instead as a literal character. So let's see what happens now. Now I get a match, and I'm told that the match starts at location sub 4 and goes up to but not including location sub 5. And that makes sense. So A is location sub 0, 0, 1, 2, 3, and my caret starts at location sub 4 and goes up to but not including location sub 5. Okay, so that is the meaning of backslash when it's used as part of a regular expression. It turns off the regular expression special meaning of the very next character. So why did I say this was some kind of wart or problem? Well, remember that a string itself, let me create S2, also uses backslash as a special character. For example, \n is the new line character, \t is the horizontal tab character. I have to type \\\, if I want to represent a single backslash character. Now S2 clearly contains a literal backslash character within it, as indicated by the double backslash. And yet when I do a search for \\, within S2, I get an error. What the heck is going on here? Well, the problem is that in this pattern string, \\ is a special character in the string itself, and so the search string here is just \. But in regular expression notation, the assumption is that if I have a \, it's going to be followed by some other regular expression character whose special meaning I want to turn off. But here, all I have is a \, with nothing following it. And so to get this to work, I need to say re.search //. That's for my first backslash within this search string. //. That's for my second backslash within this search string. And then S2. So I need to use 4 backslashes in order to search for a single backslash in S2. And this time I will get a match. I am told that the backslash begins at position sub 2 and ends before position sub 3, and that's correct. If I look at S2, the sub 0 character is this new line character, the sub 1 character is this tab character, and the sub 2 character is the literal backslash. All right, so this is madness that I have to use 4 backslashes in my pattern string in order to search for 1 backslash in this argument string here. And consequently, what we need to get in the habit of doing is to put an R, meaning raw, in front of our pattern string. Putting R in front of a string literal, that is, putting R in front of some sequence of characters between a pair of single quotes or a pair of double quotes or a pair of triple single quotes or a pair of triple double quotes, means that the backslash is going to be treated as a literal character within the string. S2 contains 3 characters. Okay, new line, tab, backslash. But if I say S3 gets R, \n, \t, \\, the R means that this should be interpreted as a raw string in which the backslash is just a backslash. And this is going to be 6 characters. Backslash, little n, backslash, little t, backslash, backslash. And if I ask for the length of S3, I get told that that is 6 characters. So, given S2, which does contain a backslash, instead of saying backslash, 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 backslash as my pattern, I can say raw backslash, backslash as my pattern. Okay, so the raw means that the backslashes are treated as literal characters. And so I'm passing 2 backslashes, a backslash followed by a backslash, as my pattern. And in regular expression notation, backslash, backslash means to look for a literal backslash character. And I did find a match. Okay, so I'm reasonably confident this is quite confusing the first time you encounter this discussion about multiple backslashes. The upshot is, though, that we're just going to get in the habit of putting R in front of all of our patterns going forward. All right, so here on slide 17 are many more patterns that we're going to test using our little program. This pattern, $, well, dollar matches the end of a string, whereas caret matches the start of a string. What we're saying here is that we want to search for lines that match the pattern start, end. That is, the start has to be immediately followed by the end. That is, lines that don't contain any characters. Let's take a look at our little program. And instead of $H, I'm going to say $. I'm also going to put my R in front. I'm now going to display lines that contain no characters, where the beginning is right next to the end. I press F5, and there are 3 blank lines in the poem. If I revert to my program, we can see what those are. All right, so there's a blank line, here's another blank line, here's another blank line. So I do have 3 blank lines in my poem. In the next pattern, this caret symbol here is followed by two spaces, which I'm not able to highlight. And following the two spaces, I'm using square brackets. Square brackets means to match one character, which is one of the characters contained within the square brackets. And within the square brackets, I can use a dash as a shorthand for a range of characters if those characters are sequential in the ASCII character set. Now, in the ASCII character set, it turns out that all of the uppercase letters are sequential. So by saying in square brackets, capital A dash capital Z, what I'm really saying is that I want to match one character, which is some capital letter. So, to summarize, this pattern is going to look for lines that begin with space, space, capital letter. Let's see what we get from that. So these are going to be lines that begin with space, space, and some capital letter. Some letter between A and Z. I'll save this and run it with F5. And notice that I've got the 4 indented lines now from the stanzas in the poem. So all of these lines begin with 2 space characters followed by a capital letter. Now, the star in regular expression notation modifies the meaning of the character immediately in front of the star. What it means is to match a sequence of 0 or more occurrences of whatever that character is. In the pattern on slide 17, the character that is in front of the star is one space character. So, in regular expressions, you never think of the star as just standing by itself. The star always modifies the meaning of the character immediately preceding it. Here, the character immediately preceding the star is the space, and the meaning of space star, that is the meaning of the character space followed by the character star, is 0 or more occurrences of spaces. Now, 0 or more means no space would be a match. 1 space would be a match. 2, 3, 4, 1,000, 10 million spaces would be a match. And consequently, what this pattern is saying is, let's match strings that start with optional indentation, that is, optional spaces, followed by a capital letter. Now let's compare that to what we did before. Our first example looked for lines that began with a capital H. Then we just looked at an example of lines that begin with 2 spaces followed by a capital letter. Now we're looking for lines that begin with optional spaces followed by a capital letter. Let's see what we get. Okay, so I'm going to say look for lines that start with optional spaces and a capital letter. I'll save this and run it with F5. There we are. So now I have every line from the poem where the first character other than spaces is a capital letter. Going back to my poem, I see that the only lines I'm not getting are the line that contains just dashes and the 3 blank lines and the 1 line that starts with spaces followed by a lowercase letter. So altogether, there are 5 lines in the poem that are not matched by that pattern. All right, the next example pattern we're going to look at is E$. Now, E is not a special regular expression character. E simply matches itself. Consequently, what we're looking for with this pattern is lines that end with a little e, that is, where little e is the last character on the line. So let's see what we find there. All right, so I'm going to change the pattern to $. And we'll save that and run it. And we discover that there are 3 lines in the poem where little e is the last character in each line. I want to point out that in the poem, if there had been a space following any one of these e's, that line would not have matched. The line only matches if little e is the very last character on each of the lines. All right, so that takes care of $. Next up, we're going to take a look at bracket, A-E-I-O-U, close bracket, and then another square bracket, A-E-I-O-U, close bracket. Well, each pair of square brackets is looking for one character, which is any one of the characters between square brackets. And so what we're saying with this pattern is, look for a line that contains a little a or a little e or I or o or u, and that character, one of those 5, has to be immediately followed by one more character, which is either little a or e or I or o or u. So in other words, lines in the poem where there's a lowercase English vowel immediately followed by another lowercase English vowel. I just want to remark that because of the font that's being used in the notes here, you might be tricked into thinking that there's a space between this closing square bracket and this opening square bracket, but that's not true. There is no space between this closing square bracket and this opening square bracket. All right, let's test out this example. So I'm looking for either little a, little e, little I, little o, little u, immediately followed by either little a, little e, little I, little o, or little u. And let's save this and run it. And here we are. So we have 4 lines that contain side-by-side lowercase vowels. Here we have tail is a match in the first line. Pour is a match in the second line. In this third line, it turns out there are 2 matches. There's an EE at that point and another EE later. All that really counts is that there is one side-by-side pair of lowercase vowels. The fact that there's another set of side-by-side lowercase vowels later doesn't really matter. And now here in the last line also we have EA as our match. Later on there's also another match, which doesn't really count. All right, in the next pattern, we're using our friend star one more time. Let's remember what star means. Some character followed by star means to match 0 or more occurrences of whatever the character ahead of the star is. Now, in this particular example, the character in front of each star is a dot. All right, and that's true in both cases. Dot, it turns out, is a regular expression character that matches any single character. So dot is going to match a letter or a digit or a punctuation character or a space or a tab. Any single character will be matched by dot. Consequently, what we're saying in this pattern is, let's match lines that contain a little a followed by 0 or more of any characters, followed by little e, followed by 0 or more of any characters, followed by little I. So in other words, the line has to contain little a, eventually followed by little e, eventually followed by little I. Now there may or may not be characters between the little a and the little e, and there may or may not be characters between the little e and the little I, because each dot star matches any number of any characters. So let's see what we get from this pattern. Okay, so I'm going to look for A followed by anything. I can think of dot star as meaning anything. E followed by anything, followed by I. Let's save and run this. Here we go. Okay, so these are the two lines that contain little a, eventually followed by little e, eventually followed by little I. So let's see if that's true. Here we have little a, eventually that's followed by little e, eventually that's followed by little I. So the first dot star is just matching the T here between the first little a and the next available little e. The second dot star is matching all the way from RS up through and including capital N, all of the characters between the little e and the next occurrence of little I. All right, so that line matches. And then in this second line, we have little a, little e, little I. All right, so in fact, star is very often used together with dot to mean any sequence of any characters, including no characters at all. Remember that space star means any sequence of spaces. Dot star means any sequence of anything. In this next example, we are using square brackets, and we're using a caret symbol inside of square brackets. Now, square brackets ordinarily mean to match one character from the set of characters defined in the brackets. But as a special case, if you use the caret as the first character inside square brackets, that means to match one character that is any character that is not one of the characters in the set. Okay, so caret and then some characters ABC means to match one character, but the character that's matched can be anything other than A or B or C. What we're saying here is not little t. Okay, so the square brackets here is going to match one character that is not a little t. And we're looking for that character starting on the beginning of the line. We're also throwing in a star here, so we're actually matching lines that begin with 0 or more non-little t's all the way up to the end of the line. All right, this looks pretty convoluted, but what it's saying is that between, let me erase this yellow stuff. What it means is that between the beginning of the line and the end of the line, the only characters that we're allowed to have are 0 or more characters that are not t's. In other words, to say this in English, we're looking for lines that don't contain little t anywhere. Let's see what we get from that. Here's our poem, and I'm saying, look for lines that begin with 0 or more non-little t's all the way up to the end. Let's see if we can figure out what we're going to get. All right, so the first line does contain a little t, so we're not going to get the first line. We are going to get the second line because there's no little t's in here. We're going to get the blank line because a blank line does contain 0 little t's. We get by Lewis Carroll. We get this other blank line. We're not going to get the line containing doth. We're not going to get the line containing tail. We're not going to get the line containing waters. Here we go. On every golden scale, there's a line that does not contain any little t's. And in fact, if we look at the last stanza, every line in here contains a little t. So let's see what we get. Save this and run it. And there we go. So these are the only lines, including blank lines, that don't contain little t's. We've got a total of 6 matching lines, including the 3 blank lines. Okay, now before we look at this final example on the bottom of slide 17, where we're looking for a literal dot, that is a literal period character, I'd like to do a somewhat simpler example of using the dot as a special character. Let me pull the poem back into view. Here's our poem. If I say E dot S with no dollar, what I'm saying is I want to look for lines that contain a little e followed by exactly one character, which could be any character at all, followed by little s. Let's see what we get. Okay, so in each of these lines, let's remind ourselves the pattern, E dot S. So in each of these lines, we have somewhere a little e followed by a character followed by an S. So for the first line of output, the dot is matching the little r. For the second line of output, here's our little e followed by a character followed by an S. And the dot is matching the space character. I happen to notice that we have a second match in this line, although the second match doesn't really matter. But here we have a little e followed by an M followed by an S. All right, so that's what dot all by itself means, is to match any one character, whether it's a letter or a digit or a space or a tab or whatever it might be. All right, now let's take a look at that last example on slide 17. In this last example on slide 17, we're searching for a literal period. We're using the backslash to cause the dot symbol to just be treated as an ordinary dot. That is a literal dot. Now this poem, I guess Lewis Carroll is an excitable author. If we look at this poem, there are no literal period characters anywhere in it. So if I search for a literal dot, I should get no lines of output. Okay, but let's modify the poem to make the poem a little less excitable. Let's add a period here, or change the exclamation mark to a period in these 2 places. And let's save and run our program again. And we see that we got the 2 lines that contain a literal period character. What if I got rid of the backslash? What if I said, look for lines? Well, dot means to match a character, any one character. So what line should I get if my pattern is any one character? Let's see what happens. Almost looks like I got everything. Not quite, though. Here's the poem. Notice that what I didn't get were the blank lines below the, or between the dashed line and the author, and between the author and the first stanza, and between the first and second stanzas. Okay, blank lines, at least in this poem, don't contain any characters. Right, so here's a blank line. It contains no characters. Therefore, it does not match a pattern that is searching for a character. Now, all the other lines do contain a character. They happen to contain a whole lot of characters, but they do contain a character. So the first line contains a character. The second line contains a character. The fourth line, contains a character. The sixth line contains a character, etc. So the only lines not displayed are the 3 blank lines, maybe to be really correct, I should say empty lines, that don't contain any characters. Okay, so that's the basic regular expression characters. Any character that's not a regular expression character just matches itself. Caret means the start of a string. Dollar means the end of a string. Dot means any single character within a string. Square brackets means exactly one of those characters. Or if I use a hyphen, it means exactly one of the characters in the range. But with the exception that if I use a caret as the first character inside the square brackets, it means any one character that is not one of the characters in the set or the range. Star modifies the meaning of the character in front of it to mean give me a match of 0 or more occurrences of whatever that is. Star is very often used together with dot. Dot star matches any number of any characters. And then we have backslash that causes the special meaning of the next character, that is a caret or dollar or dot or square bracket or star, to be turned off so that that character is just treated as a literal character. Here on slide 18, we have some of the so-called extended regular expression characters. For example, the vertical bar symbol means to match either the regular expression on the left or the regular expression on the right. A regular expression in parentheses matches whatever that regular expression matches, and also creates something called a pattern group. These pattern groups are numbered from group 1 through group 9, and I can refer to a particular group by using backslash followed by a number. So backslash 1 would match group number 1, backslash 2 would match group number 2, and so forth. Somewhat similar to the star, we have plus, which modifies the meaning of the regular expression in front of it to mean one or more occurrences of that regular expression. And question mark, which again modifies the meaning of whatever's in front of it, meaning to match either 0 or 1. Okay, so star matches 0 or more, plus matches 1 or more, question mark matches 0 or 1 of whatever the preceding regular expression is. Let's see examples of these things. Okay, so on slide 19, our first example is using the vertical bar symbol. And what that pattern is saying is, let's search for strings that contain how with a capital H or Nile with a capital N. So if a string contains either of those two possibilities, that string will match. Let's try that out in our code and see what we get. All right, here's our poem. And we're searching for how with capital H or Nile with capital N. And what we get is 5 lines of output. 4 of these lines do contain how with a capital H. 1 of them contains Nile with a capital N. So that allows us to look for 2 alternative patterns in a single regular expression. Next, we have an example in which we're creating a group in parentheses. Now, the square brackets mean what they meant before. Square brackets mean to match one character, which is one of the characters in the brackets, that is either a little a, or a little e, or a little I, or a little o, or a little u. The parentheses around that cause the match to be treated as a group, and by using \1, what we're saying is, having found a match in the parentheses, we want to also have exactly that same character appear again. This is different from the example we did earlier, where we looked for a lowercase vowel followed by another lowercase vowel, because in this example on slide 17, we weren't being specific about what that second lowercase vowel could be. So we could have things like AE or EO, combinations like that. But in this case, in this example, we're matching a lowercase vowel followed by exactly the same lowercase vowel again. So whatever the first match is in parentheses, we have to match that again. Let's see what we get in our output. Okay, so match a lowercase English vowel, A, E, I, O, or U, and create that as group number 1 in my regular expression. And let's immediately have the same character again afterwards. So let's run this, and we only get one line of output because we only have one line where there is side-by-side identical lowercase vowels. Okay, now I did just realize something. I want to, just to be consistent, let me replace the exclamation marks in the poem. All right. So we've taken a look at the vertical bar. We've taken a look at the parentheses and using \1 to match that first group. In this third example, remember that dot matches any one character. So by putting 3 dots inside parentheses, what we're saying is match some sequence of 3 characters, and that's going to be a group because it's in parentheses. That's going to be group 1. Dot star is how we match any number of any characters, and \1 is how we say, okay, now I also want to match group 1 again. So in other words, what we're doing is we're looking for some 3-character sequence that occurs at least twice within the string. And there may be any number of characters separating those 2 occurrences. Let's see if there are any such matches. Okay, so 3 characters, ... That's group number 1. Now, following group number 1, we can have any number of characters, and then we will require there to be another copy of group number 1 in the string. Well, let's run this guy. Okay. Now, the first output is the line that has all the dashes. And that's pretty straightforward. We have .. That's group 1. And that's immediately followed by .. So we have 2 occurrences of .. in that line. Similarly, the line that contains the author has space, immediately followed by space again. These next ones are a little tougher to see. Actually, this third line is pretty straightforward. We see that we have THE, later followed by THE. Now, actually, to be really precise, what's being matched is space TH as the 3 characters, creating the group, and then later on we have space TH again. In the third example, if we stare at that for a little bit, we discover ES space followed later by ES space. So each of those 4 lines has some 3-character sequence at least twice in the same line. In the final example here on slide 19, instead of one sequence of 3 characters as a group, we're matching one character as the first group. The character immediately following that is the second group. The character immediately following that is the third group. Then we have ... matching any number of characters. Then we're looking for the same 3 characters that we matched in the groups, but in a different order. So we're matching the third character first, followed by the first character, followed by the second character. So let's see if we get any matches from that pattern. All right, so we're going to have separate groups for the first character, the second character, and the third character in some sequence of 3. Then we're going to have the third character first, followed by the first character and the second character. Okay, well, again, these first 2 lines are obvious. we have characters 1, 2, 3, followed by characters 3, 1, 2. Likewise, characters 1, 2, 3, followed by characters 3, 1, 2. Now things are going to be a little trickier. You might think that we have th space followed by space th, but you can't have the same character in both matches. The actual matches are here. E space L. Okay, so E is character 1, space is character 2, L is character 3, and then we have L, E space. Okay, so E space L followed later by L, E space is a match. Here we have HIS, 1, 2, 3, followed by SHI, 3, 1, 2. And then the last line we have N space E, 1, 2, 3, followed by EN space, 3, 1, 2. What in the world would you ever use this for in real life? Well, imagine that you were dealing with, let's say, a list of customers, and all of those customers had, let's say, a first name, a middle name, and a last name. Well, you might be interested in searching through records for lines containing first name, middle name, last name, followed later by last name, first name, middle name. Okay, so you've got the same information, but in different orders. And so this business of grouping and then using the \1, \2, \3 to match the groups is very useful in some situations that do actually arise. And in fact, if you think about that particular example, it's really hard to imagine any way of dealing with it that doesn't use regular expressions. Here on slide 20, we have some more examples, this time doing some lexical analysis, that is what's called token validation. You can imagine using regular expressions like this for testing whether the input that you got from some user or from some variably formatted text input file is at least in a valid format before you try to use that input value for some purpose. For example, in the C++ language that we'll look at in FC2, a base 10 integer is required to start with a decimal digit between 1 and 9, and then it may or may not be followed by additional digits between 0 and 9. And so that's what's indicated by the 0-9 star in square brackets. If we want to confirm that a particular string is a valid C++ base 10 or decimal integer, then it needs to match that pattern. C++ also provides octal or base 8, as well as hexadecimal or base 16 integers. In C++, an octal digit starts with a 0, and then there may be additional digits between 0 and 7 following that 0. So to match a base 8 octal integer, we have to start with a 0, and then we may have additional digit values between 0 and 7. As a trivial point, notice that the value 0 all by itself is treated by the C++ compiler as an octal value rather than a decimal value. That really doesn't matter because the value 0 is the value 0 regardless of what your number base is. For base 16 numbers in C++, you have to start with a 0 followed by an x. Now the x may be lowercase or uppercase, so we're using a pair of square brackets here containing little x and big X as the possible alternatives. Following the x must be at least one digit, hexadecimal digit. Now a hexadecimal digit can be either a value between 0 and 9 or a letter between A and F. A represents 10 up through F, which represents decimal value 15. And those letters can be either lowercase or uppercase. There has to be at least one, and there may be more than one. Consequently, you're using the plus regular expression character following this square bracketed pattern. to indicate that we have to have one or more hexadecimal digit value between 0 and 9 or between A and F, lowercase or uppercase. It turns out that Python has the same form for hexadecimal digits that C++ has. So if I type the value 0x41, this is recognized by Python as an integer value. It's in hexadecimal format. And so that's a 4 in the 16ths place and a 1 in the ones place. So that gives me 65 in base 10. For octal, rather than just using a leading 0 in Python, I have to use a leading 0 followed by an O. And then I specify my octal digits, my digits between 0 and 7. If I want to get 65, let's see. The columns in octal are the ones column, the eights column, and the 64s column. So 64 would be a 1. No eights would be a 0. 1 would be a 1. So this is the base 8 representation, the octal representation of decimal 65. Now, the X can be uppercase. Likewise, the O can be uppercase. But I think you can see why stylistically people prefer to use the little o when they define octal values. Depending on the font that you're using in your development environment, it may be very difficult to tell the difference between 0 and capital O. Now, Python also has another way of representing integer values that C++ does not have, which is cool. We can say 0b and then give a binary representation of an integer value. So if here I have a 1 in the 64's place, then a 0 in the 32, 016, 08, 04, 02, 11. That is a binary representation of decimal 65. Oh, I just glanced at this. I was wondering why in the world my octal 41 didn't display as 65. Well, because I'm an idiot. That should have been 0, 0, 101 to get 65. Okay. Now, a Python identifier that you can use as a variable name or function name or class name in a Python program has to start with either a letter or an underscore. So I've got my starts with, and then I've got my square brackets indicating either lowercase letter or uppercase letter or underscore. And that can optionally be followed by lowercase letters, uppercase letters, digits, and underscores in whatever order. So I have star here in that square bracket to indicate that I can have additional letters, decimal digits, or underscores following the first character that has to be a letter or an underscore. Okay, so when I get some input from some source, whether it's a user or a text file, I can use regular expression patterns to validate whether the stuff is in the correct format before I try to make use of that and do any processing. Let's suppose you ask a user what their social security number is. Well, that pattern is going to have to look like, starts with 3 digits, and then a literal hyphen, and then 2 digits, and another literal hyphen, and then 4 digits. So that would be a regular expression just using basic regular expression notation to recognize a validly formatted social security number. 3 digits dash 2 digits dash 4 digits, and on and on. Okay, so that gets us to the conclusion of our regular expression examples. Next up, we're going to take a look at web scraping. The idea of web scraping is you want to go out to a particular website and you want to pull down the entire contents of that website as text that you can then parse and manipulate using a combination of regular expressions or various other web scraping tools. We'll take a look in particular at something called Beautiful Soup. Okay, so let's find some interesting data on the web that we can scrape. Of course, in finance, we're always concerned about the Treasury yield curve. If I Google for the Treasury yield curve, all right, I will find, let's see, daily yield curves from treasury.gov. That sounds nice. And what I will get is a table of business days and the interest rates for the various Treasury interest instruments. By default, I just get the current month. I can ask for the entire year so far, 2019 so far. Click Go. And now I have a quite extensive table dating back to the first business day of this year, January 2nd, and continuing through probably the previous Friday. Okay, so continuing through Friday, September 20th. Well, this is a very nice table of information that we probably would like to have access to. And the hard way of scraping this information is, within our Python code, we can open a connection to the web page. This is basically like opening a file, except we use a different function, and we specify the URL for the web page. Here is the URL right here. You would see that if you just looked at the top of the browser. It's the same information that we have there. Then we will read the source of the web page. You probably know that if you're looking at a web page, you can right-click and view the page source. In here, we'll discover that, well, we've got a lot of gibberish, but we've also got a table of all this yield curve data if I scroll down far enough. So here we have the column labels, date, 1 month, 2 months, etc., and the interest rate values, 2.51, and so on. So this table information is available to me from this website. And if I download this source, if I download this HTML code, I can extract this table. All right, so here on the right-hand screen on slide 23, we've written the code for doing the steps described here on slide 21. First, in order to be able to open the connection to the web page, we're going to need the URL open function from a module named urllib.request. So we're going to import that, and then we're going to open our connection to that website. What we get back is the connection to that website, and from that connection we can read the data. Now the data comes back to us as what's called a byte string. We need to convert that byte string into an ordinary string by using the string conversion function and specifying that the encoding of the byte string is UTF-8. That's the most common coding format for documents on the web. The date string is something that we can directly edit. What we're going to do here is open an output file, yctemp, which stands for yield curve temp.txt. We're going to write the data string into the file and then close the file. Once we have that string stored in a file, we can edit the file and look for patterns that we're interested in, and then we can write code that will parse out the pieces of information that we want. Regular expressions are often a very important tool for doing this parsing of the information contained in the file. So let's see what we get if we run this so-called hard scrape Python program. Here is my program. I'm going to press F5. And it runs. All right, I didn't get any output because the output was written into a data file. Now, I have on my system something called Cygwin installed, which is a Linux-like environment that I can use on Windows 10. This is my Linux-like terminal window. And in here, if I look at my files in reverse chronological order, I see that I do have this yctemp file that was just created. I happen to be recording this on Sunday morning just before 9 o'clock. I can edit this file with an editor that is capable of handling files that are at least half a megabyte in size. And my choice is VIM, VI improved. You need to have the ability to use some editor that can edit arbitrarily large files in a convenient way. So I'm going to edit yctemp. And here we are. Now, when we read the HTML from the website and converted that into a plain string, one effect that we got is that the formatting is a little bit neater than what we saw when we looked directly at the source code on the website itself. Now, we're interested in this yield curve table. We know that September 20th is the last thing in the table. So let's search for September 20th of 2019 and hope that there's only one occurrence of that pattern in this file. That will help us narrow down which part of this HTML file we need to look for our table in. If we look back at our website, we see that the format of the date is month, day, year, 2-digit year, 2 digits for the month and 2 digits for the day, separated with slashes. So let's try searching for that pattern. All right, so I'm going to search by typing slash in VI for 09/20/19. Well, okay, so this is a little VI thing that doesn't matter if you're not using the VI editor, but you initiate a forward search in VI by typing the /. And one implication is that you can't use forward slashes directly in the patterns that you're looking for unless you put backslashes in front of them. Like you would have to do to turn off the meaning of a special character in regular expression notation. All right, so by typing 09//20/19, I was able to find that particular pattern. And if I search for the next occurrence of that pattern by pressing little n in VI, aha, I get told that the search hit the bottom and wrapped around from the top and came back to the same pattern that I already found. So that's good news. That means that there is only one occurrence of 09//20/19 in this file. I must therefore have found the table. And certainly if I look in the vicinity of that date, I see things like 1.95, 1.94. These certainly look like interest rates, so that gives me some confidence. In the VI editor, if a carriage return character appears in the file, it's displayed on the screen with this symbol, or this pair of symbols, this pair of characters, caret capital M. Okay, so that implies to me that everything I'm looking at on my screen here is part of a single line. Let me go back to the beginning of this line and see what I find. Okay, so I'm going to go to the beginning of the line. And, oh, well, that's convenient. At the very beginning of this line, I see that this line contains a table. That's good. A table is what I'm looking for. Now, if I Google for what table means in HTML, I'll discover information about the formatting of a table. And a table contains some number of table rows. Here I have TR, which is the beginning of the first table row in this table. I know that by Googling. I'm not an HTML expert, so I looked this up. And the first thing in this table row is table heading information. All right, so the table heading information, well, it's a little bit messed up here, but the table heading information contains date, and then 1 month, and then 2 months, and so on. So that certainly looks like the first row in my table. Then the second row in my table contains table data. Here's my first day of the year, and here's my 1 month interest rate, my 2 month interest rate, my 3 month interest rate, etc. So I have definitely found the table that I want. Unfortunately, there's all kinds of clutter. There's all kinds of HTML code clutter that I want to get rid of, because I really only want the data that's contained in here. I don't want all of this table, TR, TH, TD mess. I just want the data from within the table. Well, there is structure to this HTML mess that I want to get rid of. For example, here I have left angle bracket TH, eventually concluded by /TH right angle bracket. So I can search for those kinds of pairs and figure out which part of this table heading is the data that I'm interested in. Regular expressions are going to come to the rescue for me here. Okay, so I have downloaded the file, examined the file with an editor, VI in my case, and now within Python I can use various regular expression functions to search for patterns, and then to use substitutions to get rid of the part of the patterns that I don't want. The substitution function allows me to specify that if I find some regular expression pattern, I want to replace that regular expression pattern with some replacement string. The third argument here, stir, is the input string that I'm doing this substitution in. All right, so sub is going to enable me to throw away parts of each string that I don't want. And then, once I have winnowed each line down to just containing data, I can use the regular expression split function to split the remaining parts of the line into a list of strings that are just data. So let's see how we go about doing that. Here we have a program called last line columns. What this program is going to do is to just display the columns within the last line of data from my table, just as an illustration. So we're going to get the columns from the line for September 20th of 2019. All right, so for each line in my input file, I'm opening my yctemp.txt file as input. For each line in the file, I'm going to look at that line to see whether that line contains my table class equals tchart notation. If I look back at the file, I see that this line containing my table starts with table class equals tchart. Actually, I should search for table class equals tchart to see whether that pattern occurs more than once, and it doesn't. Okay, so there's only one line in here that starts with table class equals tchart. So in my code, I can search for that line that starts with, or that contains, table class equals tchart. And then, having found that line, I'm going to throw away stuff at the beginning of the line. I'm going to throw away stuff from the end of the line. I'm going to get rid of stuff between the data columns. And then finally, I'm going to split those data columns into a list. I'll close my input file and display the column. And that should be the columns of data for September 20th of 2019. Now, obviously, there's a lot of detail going on there, but let's just run the program first to see whether it does what I claim, and then we'll come back and analyze it more carefully. Here is my program. And I'm going to run it. And yay, I got what I wanted. I got a list of the data values from the last line in the table for September 20th of 2019. And here I have 12 interest rate values. Now at this point, these things are all strings. I would need to convert these interest rate strings into interest rate float numbers in order to be able to do some analysis with these. But so far so good. So let's figure out on a step-by-step basis what these various sub-functions are up to. Here is a version of the program in which I have added print statements after each of the searches and substitutions so that we can see exactly what's going on. Okay, so here on the right-hand side now, I have a version of last line calls that throws in these print statements as well. Actually, I want to comment out a lot of these and reintroduce them as we go through the various parts. Okay, so for each line in the input file, we're going to search the line to see whether it contains this pattern. Now, by the way, there are some punctuation symbols in here. There's a less than symbol, there's an equal sign, there's a double quote, but none of those, if you take a look at the regular expression character table, none of these things are special regular expression characters, so they're just looked for as literal characters. All right, so we're looking for less than symbol, table space, CLASS equals double quote T dash chart. And if we find that, we are going to display the line. All right, first I'm going to print out a message that we are displaying the line, and then we're going to display the contents of the line. In order to have two print statements on the same physical line, I've used my semicolon in here so that I can have two logical lines on the same physical line. All right, so let's just do this part first. I'm going to save this and press F5. And, all right, well, we got this huge squeezed line. All right, 1,277 lines. Well, that is that huge long line containing the table. I'm going to click cancel because we don't really want to look at that. I also got an error message because I just realized that even though I commented out the creation of the calls variable, I'm still trying to print the calls variable. So let me comment that out. All right, so let's see what we're doing with this first substitution function. Well, what I want to do is to get rid of everything on the line up to the very last row in the table. Dot star matches any number of any characters. And dot star is what's called greedy. That is, it will match as many characters as it possibly can until there is only one occurrence left of less than symbol tr space, followed by some other characters, followed by row double quote. And a greater than symbol, a less than symbol, TD. And then we have things that are not greater than symbols, any sequence of those. Good heavens, what's that all mean? Well, let's take a look at our file in VI. And let's go to the end of this line. All right, because it's the very last row in this table that I'm interested in displaying. And that's the row that contains the date September 20th of 2019. So starting from there, if I go back, where is the beginning? Okay, so here is the beginning of the row that contains that. And that row is identified by left angle bracket tr space and then class even row. All right, in my program, I'm looking for less than symbol tr space, and then I don't know, some of these rows are even rows, some of these rows are odd rows. Let me find an odd, oh, here's an odd row, all right? Some of these rows are even rows, some of these rows are odd rows. This last one in the table happens to be an even row, but since I don't know on a given day whether that last row is going to be even or odd, I'm using dot star to match either even or odd. It'll match anything. And then I'm looking for ROW, double quote, and a right angle bracket. And that's what I see here. I've got ROW, double quote, and a right angle bracket. So that is how I identify that I have found the last row in the table. The dot star matches everything up to that point. See, this dot star matches everything else on the line up to this point. Now, I also want to get rid of the left angle bracket TD, blah, 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 up to this right angle bracket. And so to match all that part, I'm saying, okay, starting from left angle bracket TD, all the way up to the next right angle bracket. And in order to make sure that I don't go too far, I'm saying match left angle bracket TD followed by any sequence of characters that are not right angle brackets followed by a right angle bracket. All right, so here is my left angle bracket TD, and then I have characters that are not right angle brackets, all right, PE equal, double quote. These things are not right angle brackets, so the star is going to swallow up all of these until I get to the right angle bracket. I want to throw all of that text away so that the only thing remaining is the line starting from 09/20/19. All right, so let's see whether my program does that successfully. I'm going to throw away everything in the entire table up to the right angle bracket just prior to 09/20/19. And then I'll print that out. So let's see if that works. Cool, it worked. I got almost the entire table thrown away, except for the part starting from 09/20/19 up to the end of the table. All right, now I need to be a little clever here. I need to figure out how to have a consistent separator between these data values that I can then use for my split. Well, I definitely don't want the last part of this line. So let me just get rid of the closing tag for TR and the closing tag for the table. That's going to be the second substitution that I do. Okay, I want to get rid of the closing tag for TR and the closing tag for table, and everything after it. Now, what is everything after it? Well, everything after it is this stray carriage turn character that I also want to get rid of. All right, so let's try that now. We'll get rid of left angle bracket / TR right angle bracket, left angle bracket / table right angle bracket, and then the carriage turn character all the way up to and including the new line character at the very end of the line. Save that and run it. Okay, good. So now I have, starting from September 20th of 2019 up to the last closing table data tag. And I've gotten rid of everything after that point. The last substitution I want to do is to get rid of all of the closing table data tags. Okay, so I want to get rid of all of these things. Left angle bracket / TD. Left angle bracket / TD. If I get rid of all these left angle bracket / TDs, then what I can use as my separator between all of the values is this left angle bracket TD class blah 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 up to the right angle bracket at the end. I can use that as my separator, and that's how I'll do my split, and I'll just have the data values left. Okay, so let's get rid of all these /TDs. All right, so all the /TDs are gone. Notice that I have valid data as the first thing in this remaining string, and valid data as the last thing in this remaining string. And separating all of the data strings, I have this pattern. Left angle bracket, TD space, right angle bracket. And so that's the last split that I'm going to do, or that's the split that I'm going to do from the left angle bracket followed by everything that's not a right angle bracket up to a right angle bracket. That's what I want to use as my split field in line 4 to get back this list of columns. I should print, well, I am going to print those columns then. All right, and so there we are. So I've got just the last rows data fields. So this program just displays the data fields for the last row. I could modify this to display the data fields for each row in the table. And then from there, I can change the interest rate strings to interest rate floats and do whatever computations I'm interested in doing, or plotting, or whatever it might be.